Hello, welcome to my VLDB presentation. My name is Binhang Yuan. I will introduce our work about tensor relational algebra, a new abstraction for distributed machine learning system design. This is a work I did under the supervision of my PhD advisor, Dr. Chris Jermaine. I also would like to thank all my colleagues from Rice and Arizona State University. Before we get started, I want to briefly summarize the design of current machine learning systems, such as PyTorch and TensorFlow. In general, it includes a front end that a user can declare her model, and the system would use its auto-differentiate engine to generate the computation graph for its gradient descent optimization. On the other hand, such systems also include a backend that is responsible for the execution of this computation. In a distributed environment, common parallel strategy provided by such system include data parallelism, pipeline parallelism, and operation partitioning. So what is the problem in the current design? Well, its backend is only optimized for particular hardware like a GPU and communication paradigms like parameter server and all-reduce for data parallelism without considering being declarative. In other words, a user usually has to manually choose the distributed execution strategy, assign the computation to a hardware, and even manage the communication for synchronization. This sounds a lot like an optimizer's job in a classic database system. In fact, database systems are very good at declarative and parallel distributed query processing. However, database is built on top of the set theory. If we directly borrow this idea, it would compromise the performance for machine learning computations. So in this paper, our fundamental goal is to bridge this gap. At the highest level, our solution can be summarized as this. We store tensors required by machine learning computations as special relations. Then the machine learning computation can be included as a group of join, selection, and aggregating operations with the extended lambdas. And the computation graph for SGD iteration can be encoded as a query plan. Then the system will run a database-style optimizer to automatically determine the execution in a distributed runtime. Let us consider matrix multiplication in a fully connected layer as an example. Assuming matrices X and W are partitioned as blocks and stored in two relations. Given a three-worker cluster, the system can decide to broadcast matrix X and partition matrix W. This actually follows the broadcaster join schema in distributed query processing. Then the system can do some local join and apply the multiplication on each block. And finally, the system can do the local aggregation and apply the addition on each block to generate the final results. To be more concrete, our work attempts to answer three fundamental questions. First, what should be the right abstraction for expressing distributed machine learning computations? Our answer is a declarative interface called tensor relational algebra, TRA in short. Second, what is the right abstraction to implement such formalization, especially for distributed runtime? Our solution is design and implementation algebra, IA in short. Lastly, what are the unique operations we can adopt for this implementation abstraction? For this, we implement a rule-based relational optimizer. Formally, the tensor relational algebra is based on the tensor relation, which includes k-value pairs, where the k can represent the index of a chunk of numeric values. We support UDF-style operations so that machine learning operations can be implemented based on this abstraction. We can also show this is expressive enough to represent any tensor manipulation allowed by the Einstein notation. Here is the complete list of TRA operations. Next, although TRA can formalize machine learning operations, it is not sufficient to specify different distributed implementations. Implementation algebra is to bridge this gap. Conceptually, the system should choose which distributed algorithm to use. IA is about to provide candidate implementations for the later optimization. Technically, IA extends the tuple in TRA with a site information to tell which worker stores the current tuple in the cluster. On the other hand, it also modifies the TRA functions a little bit. In general, The IA operations can be categorized into two classes. The first class is responsible for aligning tuples to different sites in a cluster, where we include a broadcast and a shuffle operation. The second class is inherited from TRA as local operations. The only difference is that the operations can only be applied on tuples with the same site information. Lastly, I will talk about the optimization for these abstractions. We define a group of equivalent rules between different IA expressions. Such rules can come from classic query optimization theorems based on kernel function composition and equivalent partitioning of a distributed storage for relation. We call such rules simple equivalent rules. On the other hand, we also have some domain-specific equivalent rules based on some analysis of machine learning computations. For example, the target TRA represents matrix multiplication can be implemented in 3 ways in IA, which perform differently in different situations. They are considered equivalent for this particular machine learning computation. Lastly, given the candidate IA expressions, we should estimate the execution cost. In the current system, our goal is to minimize the network traffic during the execution of the IA. We consider more advanced cost model as an interesting future work. Lastly, I want to talk about our experiments to justify our design. We try to answer 2 questions in this section. First, can the proposed system provide competitive end-to-end performance? And second, would the proposed optimization generate efficient plans under different settings? The short answer is yes to both questions. To be more concrete, I would like to show the result of one benchmark we have in the paper, feed-forward neural network. For this computation, we have different model dimensions for different data sets. In the first workflow, data parallel is the optimal communication paradigm. Our cost model can find such a candidate plan. Its end-to-end runtime is as good as PyTorch and TensorFlow. Notice that TensorFlow and PyTorch are specially optimized for data parallelism. In the second setting, a model partitioning schema is the optimal plan. Our system is able to find this from the candidate IA expressions, and for the end-to-end performance, it outperforms all the other baselines in terms of the execution time. Okay, great. Thanks for listening to my talk. I'm happy to discuss any question about this paper, and you can also reach me by this email. Thank you again.